Hello and welcome to another physics post. This one is on thought experiments. When you are always bored with anything you understand, you will gravitate towards ideas which are impossible to understand. In general, nonsense. Thought experiments provide a wealth of nonsense. For example, Epimenides' paradox, the crocodile dilemma, and just about anything that Einstein said, or anything you find about paradoxes of relativity on YouTube. As you will see in this video, most of the teaching you find on the internet about relativity and Einstein's paradoxes, it's horrible. Now, why do I think I have the ability to speak on this issue? Because I have studied these issues experimentally. I was in the physics community for 20 years and I specialized in accelerator physics. That is applied relativity, as in you do experiments with particles on relativity. That's all I did. That's what we do. Now, astronomy it's sort of like applied relativity, but where you don't have a controlled experiment. In accelerator physics, you have controlled experiments. And if your theory doesn't work, then your results are not going to work. So it's not just where you're telling a story about some data. It's a real experiment. That's why I understand that the sort of teaching about relativity, even from, I've seen Stanford professors on YouTube, telling stories that an accelerator physicist, it would make them cringe. You have to understand the difference between literal and figurative concepts to talk about relativity. And by the end of this talk, I hope you understand how much nonsense is being taught on the internet about these issues. So, the first thing to understand about paradoxes, the ancient Greek ones or Einstein's paradoxes, is that they arise when you do not think outside of the box which defines the problem. So that is the sole heuristic purpose of a paradox. But they are, as you can see from bad teaching, they are frequently misused. So when the paradoxes of relativity are taught as fact, students are given a feeling that they have learned something when they haven't actually learned anything. They've actually missed the lesson. They are given a false confidence in their understanding of a counterintuitive logic puzzle composed of imaginary situations, while gaining no understanding of the subtleties required for the application of the theory to real data. All that the student has learned from these paradoxes is how to feel clever while being gullible, how to throw his common sense in the trash, how to abandon himself to faith in a model, and in a fit of double-speak, teachers will even tell their students that despite the fact that the paradoxes demonstrate a contradiction with common sense, they are not really paradoxes. So when this sort of teaching spreads, even the teachers, they don't understand what they're teaching. This is really frustrating to see when you understand what the lesson is meant to teach. That the paradoxes are results of errors in thinking, not that they are hoops you have to jump through to detach yourself from your intuition. Okay. Relativity is not the only lesson of physics in which this subversion of basic sense is encouraged. Consider the simple example of a man dropping a ball as he runs along a street. a teacher will show a picture of a ball falling in 3 different paths. When he drops it, will it land behind him? Will it land next to his foot when he's running, or will it land in front of his foot because of his forward motion? And if you ask physicists if the ball falls straight down or if it follows a curved trajectory, they will all say it follows a curved trajectory. While if you ask non-physicists if the trajectory is curved or straight, they mostly answer straight. So who is right? What's shocking about this is that the non-physicists were actually more right by saying that the trajectory was straight. The ball doesn't drop exactly straight down, but the curve of the trajectory is so small that one can't see it or measure it. A curved trajectory would only be appropriate if the man running along the street is faster than a cheetah or on the moon. So, with this example, physicists believe in a model they have learned more than they believe in their daily experience with gravity. This is taught even at the high school level, and many students, I'm sure, rebel against this way of thinking because it's stupid. Next, consider quantum mechanics. Physics teachers tell their students that there are old models of atoms which are incorrect because our newer models require the counterintuitive interpretation that particles literally exist as a cloud of probabilities until they are measured. This statement is actually false because there are many ways to describe a quantum system, and given certain interpretations, the older models, which are more intuitive, are consistent with the newer models, making them superior with respect to both qualitative explanatory power and with respect to quantitative predictive power. The lesson that many physics students are encouraged to absorb is that qualitative explanatory power doesn't matter, and that all you require to understand something is a quantitative model with predictive power. But we have, as I hope to show in my future videos and in this one, there are so many examples where you can get things so wrong by putting too much faith in a quantitative model that you don't understand qualitatively. You have to have both the heuristics and the math right. You can't understand just one. And a lot of our testing only requires you to understand the math. This has big impacts on the quality of the sorts of researchers that our system can produce. So in this example of quantum mechanics, I want to show that instead of straightforward examples and explanations that suffice for most situations, physicists will tend to prefer counterintuitive, literal interpretations which detach the student from a kinematic sense of motion and time, and which often lead them down a road towards misinterpretation of basic things. The result of this system of instruction is so extreme that there are whole branches of physics today that either have no connection to experimental reality, like string theory, loop quantum gravity, or they draw inferences which go far beyond what the experimental data suggests. For example, Gell-Mann's nuclear model with quarks. It doesn't have applications in any sort of real nuclear science. It is just a story reverse engineered from the standard model with no applications. And in some cases, it predicts things that don't actually happen. One of the hallmarks of cultish thinking is a gradual abandonment of common sense, and people who leave a cult leader often describe it as a sort of snap in which their long suppressed old identity suddenly re-emerges and recognizes all of the nonsense that they have absorbed throughout their indoctrination. These people simply stand up one day and walk away from the cult, re-emerging into the world like a person reborn as their old self. Academia has many of the hallmarks of a cult with respect to the rituals and sacrifices required for acceptance, and this is something of which both parents and students should be well aware. Children's minds are softened for indoctrination by this cult through educational materials on the internet and on TV sometimes, and the classroom that tell them that relativity is paradoxical, but that the paradoxes are not really paradoxes, or something like that. They watch videos of relativistic trains going into tunnels and ladders going into barns, and they either develop a feeling of confusion or a sense of pride over their comprehension of something abstract and counterintuitive. But this sense of comprehension is often extremely misleading, as my experience with having an experimental understanding of the applications of relativity have shown me. So, to demonstrate how one constructs an illusion of comprehension, consider the simplest possible description of relativity. Alice and Bob are particles. Bob walks into a bar holding a clock and a meter stick and runs back and forth past the bartender at close to the speed of light. This is as fast as he can run. Alice, the bartender, says, "Your clock is slow and your meter stick is short. See? Look." And she holds up her clock and her meter stick. Bob is running up and down the bar and he says, "No, your clock is slow and your meter stick is short." That is special relativity in a nutshell. Seriously. Both statements about the meter sticks and clocks are true while Bob is passing by Alice, but every time Bob turns around at the end of the bar, Alice's clock runs faster than Bob's. They jump into a car and Alice ties a blindfold around Bob's eyes. Alice steps on the gas, accelerating the car. Bob asks her, "Are we going uphill?" Alice answers, "Wouldn't you like to know?" That is general relativity in a nutshell. Seriously. So, this story accurately represents Einstein's relativity, and it certainly sounded simple, but something about it should bother you, because it's conducted in a sort of coordinate system which is impossible to understand intuitively because it's non-Cartesian and we think in Cartesian ways. A child might feel stupid for not understanding that strange story, whereas a wise old grandma might recognize that when something doesn't compute, the storyteller is at fault, not the listener. Physics tends to get this backwards. Let's try to tell the same story with different words and see if it makes more sense. You and your friend are each holding onto a long rope. You shake your end of the rope up and down, and your friend sets up a metronome to match your frequency. You start moving away from her, and she says that your frequency has gotten slower than the metronome. You move towards her, and she says that your frequency has gotten faster than the metronome. That is time dilation, stretching and contracting of time. It is merely an illusion created by your changing position relative to your friend. In real relativity experiments, you are replaced by an oscillating particle, A grandmother would understand this story perfectly well. Length contraction is also an illusion caused by changing position. If you are moving, when you look out of your window and see everything streaking past, you realize that your body would look streaked out relative to everything at rest. When your body streaks out, the distance between the particles in your body gets larger. Alternatively, one could describe your particles as contracted instead of saying that the space between your particles has expanded. Electrically, since all of your particles are charged, these two conditions must be equivalent. Yet you can't speak in two languages at the same time. And in physics instruction, this often happens, and it often confuses anyone who understands things intuitively rather than mathematically, because the math is the same regardless, but the intuition is completely different. And this should not be done because it excludes smart people, because they think that physicists just don't make sense, and they don't whenever they do this. A beam of light which travels alongside you and makes an optical replica of your body would record that your body's length is the same as it was before you started moving. A scientist would then conclude that your particles have gotten very short, like pancakes. So the takeaway from an accelerator physics perspective is that once you understand that only particles length contract and that macroscopic objects never length contract, then you will see that anyone who talks about trains contracting and fitting in short tunnels is speaking nonsense, unless this person understands that the trains and tunnels are used to symbolize the behavior of individual particles. You have to understand the difference between literal and figurative concepts, because the math is constructed around figurative concepts. You really cannot think of it as a literal description of nature. You'll get into trouble. The takeaway from this section is, be wary of people who speak of particles as though they are people or macroscopic objects. The next issue in relativity that people get wrong all of the time is the twin paradox. Everybody has seen science fiction movies featuring time travel, and we are given a sense that this is a scientific possibility. Popular science shows tell us that if you had a pair of twins and launched one of them to Alpha Centauri, when the space-bound twin returned to Earth, he or she would be much younger than his Earth-bound counterpart. You end up with a picture of an old man, an old twin, meeting a young twin. But you need to know that this is not science. This is bad science fiction. People are not particles. We have no evidence that such things happen to macroscopic objects like people, yet somehow this picture has made it into the mainstream academic discourse, and many physics students accept it as a fact of reality. I have seen this by looking at these question and answer sites on the internet where people give their answer to questions about relativity, and even people with PhDs answer these questions incorrectly because their subspecialty doesn't require this sort of understanding. I hope that future generations will laugh about this because it's laughable that people believe this. If the calculation of the twin paradox is done properly, one sees that while the traveling twin is journeying through the stars, he may age at a different rate from the warped perspective of the Earth twin, but by the time the traveler gets back home to meet his earthbound twin, time has caught up with him, and they are the same age. Depending on our preference for special or general relativity, we can disagree about when and how the traveling twin ages from the perspective of the earthbound twin. Does he age all at once when the spaceship turns around to head home? That's what you get if you assume that there is no preferred reference frame. Does he age gradually throughout the journey in a preferred reference frame? What we can agree about is that when you throw a ball up in the air and catch it, it only momentarily feels heavier than the ball you didn't throw. I think that traveling twins work in the same way. The traveling twin only momentarily appears to be younger than the Earth twin. That's what the math should imply, or, well, a person with a limited, non-intuitive understanding of these issues would draw a Minkowski diagram, and you see lots of world lines intersecting and returning to the origin. But what they might not explain to you is that you can say several things about this diagram that are conceptually inconsistent, yet geometrically possible. So, in general, an interpretation of the diagram with general relativity tells you that every time the space traveler accelerates, time slows for him relative to the Earth. Special relativity tells us that while he travels away from and towards the Earth, his clock is running slowly. A third, independent interpretation of the same diagram is that absolute space is a clock. The further away from Earth the traveler gets, the slower his clock is relative to the Earth. These three things cannot all be true at the same time, unless you say that they are all different ways of saying the same thing, which is what most people say because they are intellectual cowards. In the general relativity interpretation, each time the astronaut accelerates towards Earth, she is lighter relative to on Earth, and time slows for her. Each time she accelerates away from Earth, she is heavier relative to on Earth, and time speeds up for her. So, in this interpretation, time speeds, slows, and speeds as she lands on Earth. The problem is that there is nothing in this calculation which explicitly describes her final deceleration, final acceleration. When a mathematician forgets about the final acceleration, you end up with an old twin meeting a young twin at the end of the journey. And you have to also understand that you can't treat the traveler as a person, you have to treat them as a collection of particles. And the final acceleration has an effect on a collection of particles. A heating effect. Think of burning up on re-entry. In the special relativity interpretation, in comparison, so we're going through the three different ones. That was the general relativity, then we do special relativity, and the last one is absolute space. So in the special relativity interpretation, an astronaut's clock will tick more slowly relative to the Earthling's clock throughout their journey, and when the astronaut arrives back home, she will be younger than her twin. Unfortunately, special relativity does not tell us how to calculate the effect of acceleration, so a mathematician will often skip that step, and we will end up with a young twin meeting an old twin at the end of the journey, and this is a mistake. In the absolute space interpretation, the Earthling measures the oscillations of a laser beam clock sent to Earth from a spaceship, and the wavelength lengthens as the astronaut travels away. It shortens as she returns. While she is on the distant planet, the clock still appears to be a bit slow because the light loses a bit of energy, and the wavelength lengthens when it traverses vast distances. The person on Earth doesn't predict any sort of paradox involving old twins and young twins because he understands that the apparent changes in clock speed were clearly illusions caused by motion through space. The conclusion of all of these three different interpretations of a single mathematical diagram is that if a mathematician skips the last step of a general relativity calculation, the result will agree with the naive special relativity calculation without acceleration. If the mathematician includes the last step of the general relativity calculation, then the result will agree with the absolute space interpretation and disagree with the special relativity calculation. In the naive YouTube interpretation of the math, time within the astronaut's body is slowed when she arrives on Earth, and there is nothing describing how it speeds back up to match the clocks around her. I don't think that time can stay slowed down for her indefinitely. If time is slowed down for her, then the particles in her body are cold and will have to heat back up. In other words, her internal clock has to speed back up to the normal Earth rate. The particles have to sort of vibrate and circulate and speed back up because they've been slowed down. They're like a spring. And that is the information which is missing in popular science interpretations of the math of relativity. And it is the reason that the image of an old twin meeting a young twin is wrong. For a less wrong science fiction picture, when the younger twin descends to Earth, she is momentarily younger, but time quickly catches up with her. Since she is made of probabilistic quantum things, she would appear in the sky as a youthful muon mist and slowly solidify on the ground as an old electron woman. Now I will move on to the issue of the barn pole paradox, or the train tunnel paradox, which you will find probably 100 videos on YouTube. And I haven't watched all of them, but the ones I've seen are wrong. They give you the wrong impression of how physics works. So, the train tunnel or barn ladder paradox is a thought experiment in which relativistic length contraction is applied to macroscopic objects moving at close to the speed of light. Students are taught that in the moving ladder reference frame, the ladder fits in the garage, and in the stationary reference frame, it doesn't. The garage sees a short ladder, and the ladder sees a short garage. Then they tell the students that this is not paradoxical because the math makes sense. Perhaps we should hold ourselves to a higher standard, in which both the math and the interpretation of the math must make sense. One can either accept the strange implications of the math for macroscopic objects, or one can say, hey, We've never measured relativistic effects for macroscopic objects like ladders, so maybe we shouldn't imagine that there are such effects. Or at the very least, we shouldn't imagine that such effects could be observed by looking at the system from the side, as the drawings imply. So when I say we haven't measured this in accelerators, our only way to have a controlled experiment using relativistic concepts. And in comparison, astronomy is not a controlled experiment. It is a descriptive science. Very different. So if I break this down into 2 points, we can measure that clocks in planes run slowly compared to clocks on Earth. But these clocks are just made up of oscillating particles, and this doesn't tell us anything about length contraction of a macroscopic object. We can measure relativistic effects for small things like particle bunches, and what we see there is that the length contraction and time dilation effects only apply on the individual particle level, not on a collective level. I know this because when you accelerate a bunch of electrons to near the speed of light, the bunch doesn't get shorter, but the fields from the individual electrons do get shorter or weaker in the direction in which they are accelerated. We know this happens because, my legs are going to sleep, the longitudinal forces between charges get smaller when the electrons are going faster. This happens because the electric field of each particle transforms from a sphere at rest into a pancake, when it's going fast. And when I say that the field transforms between these shifts, I mean this also in a figurative sense. All physics, I think, is figurative, not literal. There's always something going on one layer deeper that you can't see and that is not part of your model. For a book that introduces these concepts, try Wiedemann's Introduction to Accelerator Physics. An electron bunch, as observed by an electrode or an antenna, will look a bit shorter after acceleration, but not as short as you would expect if you just naively apply relativistic length contraction to it. This shortening seems like a contradiction to what I just wrote unless you consider that this doesn't mean that the bunch actually got shorter. The fields just got squished, sort of pancaked, figuratively speaking, so that the image of those fields on the electrode is shorter. It may also seem confusing that when fast-moving charged particles encounter a series of magnets that cause them to wiggle up and down in their trajectory, the magnets look like they have a longitudinal separation of a few angstroms from the longitudinal perspective of the fast-moving particles, while from our perspective, the magnets are several centimeters long. So this is another place where you should think of the difference between figurative and literal concepts and how you can approximate things for certain purposes by using figurative representations. So how is such a picture of contracted magnets consistent with my claim that length contraction only happens on the level of individual particle fields, not as a collective effect of a group of particles composing a macroscopic object? In this situation, the magnets didn't really contract. the magnet's particles' fields only seemed to contract in the eyes of the electron bunch, because the bunch spent less time interacting with those fields. The magnets didn't contract in any sense that I can think of. So if you are passing by me with your ladder at the speed of light, or in your train on YouTube, I don't think, gee, your ladder looks short, or your train looks short. No, you and your ladder look completely normal. But if I could look at you through a microscope, in principle, I would say, my goodness, your particles look frozen and very short. They look in one dimension. They're frozen in one plane. They look like pancakes. And you would look down at your own particles through your own microscope and say, I don't know what you are talking about. Everything looks normal to me. So this is a stupid thought experiment because this conversation can never happen. But if it helps you understand the folly of applying theories of particles to collections of particles, then it's worth saying. As you carry your ladder through a barn while looking straight ahead, maybe you can create an animation of this in your mind, you would think that the barn was very short because you're moving very fast. Or you might think it's very short because my particles are contracted and that must have frozen my clock. You could think that way, but if you turned your head to the side to take a picture of the barn while you were in it, you would measure that it was just as long as a person who isn't moving. So, to me, that distinction is what the relativity of simultaneity is all about. And if you're clever, you can also connect that to the uncertainty principle. So, I don't understand why it's not taught like this. Because once you see it, you can't unsee it. And it's not that hard to understand if you can visualize it. You have to be able to visualize motion and how motion distorts what you see, but not by using Einstein's relativity, because that will completely screw you up. You need Galilean relativity. Okay, I think this is, am I getting close to the end? This is another way, there's another way in which Einstein got terribly confused, and this sort of confusion is called ehrenfest's paradox. Einstein was confused by what the radius of a spinning object should be. So he thought that relativity suggested that the radius of a spinning object would change due to relativistic effects, because the relativistic effects are operating on because he didn't understand that these effects only operate on an individual particle level and not as a collective effect. Sorry, that was badly expressed. This should be more obvious when you think about the charge density in a closed loop of electric current. The loop of wire in which the current flows does not get smaller. The particles within the loop get squished like pancakes. And when their fields are squished, they stick out further from the wire, and that is why loops of current-carrying wires have stronger magnetic fields around them than wires without currents. The fields got pancaked and squished out to the sides, outside of the wire. We can also use this logic of only applying relativity to particles to resolve the spaceship paradox. Bell's spaceship paradox. What happens to the distance between two spaceships after they accelerate? If the spaceship's length contract, then a string connecting them would snap after they both accelerate. That isn't how any other physical system behaves, so it must be a paradox, unless you realize that the paradox disappears when you only apply length contraction to individual particles and not to macroscopic objects. You can take this logic into the domain of the neutron star, another stupid concept that falls out of the extrapolations based on general relativity. So if you try to model a neutron star, you can imagine charged particles propagating around the surface of the star, and that they have fields like pancakes facing in the direction of their propagation. This reduces the repulsive force between the particles and the direction, which is tangential to the surface of the star, and such a reduction could contribute to the stability of such a star. You can model this particle beam with the concept of tunes in a giant synchrotron. And this is an alternative to the typical concept of a neutron star. For a different, and according to what I've just said, wrong explanation, just watch YouTube videos about neutron stars, trains and tunnels, special relativity, and you'll even find this in classrooms with lousy professors. Some are good and some are bad. The next topic is the application of relativity to muons, or fundamental particles, and the Earth's atmosphere in terms of cosmic rays. This is an example, a thought experiment, or a descriptive result, which is often used to demonstrate relativity. So I call this a descriptive result because it's not a controlled experiment where you are actually moving around the particles and manipulating them, seeing how they change. That is done in accelerators, where you could work with muon particle beams and whatnot. And what we learn from that is that, I learned that the way cosmic rays are often taught is very wrong, even on a site called hyperphysics, which is very often used as a reference. Many people know the story of how a cosmic ray muon streaking through the atmosphere has a short lifetime in its rest frame, but it has a longer lifetime in the Earth frame because it is moving at such a high velocity. Pedagogically, this example is turned around to demonstrate length contraction by saying that from the muon's perspective, the Earth's atmosphere is length contracted, and because it doesn't have to interact with as much atmosphere, that is why it lasts for longer in the Earth's frame of reference than it would have without special relativity. I have no issue with the description given in terms of particle lifetime. But, based on what I know about particle bunches in accelerator physics, the description given in terms of distance, a contracted distance, this is wrong, and in a fundamental way. There is no situation where a muon observer looks at a train of atmospheric particles stretching from the surface of Earth to the stratosphere and concludes that the train has gotten shorter after it has been accelerated. The distance between 2 points is defined by the speed of light. That's why we talk about light years. And nothing about motion changes that. A light year is a light year, and it is associated with a fixed distance in meters. the distance from the muon to the Earth. Oh, my legs are asleep. Can I even bring them back? Let's see. Okay. Oh! Ow. They're really asleep. Ouch. My foot is totally dead. Okay. Ow! That's not going to work. Okay. There, let's see. There. Okay. Now my legs are going to come back to life. Okay. The distance from the muon to the Earth and the distance from the Earth to the muon are the same. And this makes statements about a contracted atmosphere sound preposterous. It would be better to tell students that from the muon's perspective, the reason that the particle lives longer in the Earth's atmosphere when it is traveling quickly is because the atmospheric particles appear individually pancaked, length contracted, to the fast-moving muon. And this reduces the amount of time that the muon interacts with each atmospheric particle. So this is a figurative concept. The contraction is an illusion, but it should only be applied to individual particles, not to the whole collection of particles. Maybe you can approximate it that way, but in general, you have to be careful because you can make mistakes. I think it's generally wrong. The reduced interaction time makes the decay likelihood lower than if it had interacted with non-contracted atmospheric particles. The takeaway from this is that the length contraction of the atmosphere is not a literal contraction of the distance between the Earth's surface and the muon. It is only a contraction of the fields of the atmospheric particles, and this contraction reduces the amount of time that the muon interacts with each atmospheric particle. Of course, from an absolute perspective, the atmospheric particle didn't actually contract. It only appeared to contract from the perspective of the muon. The alternative to thinking about squished particles in a fast-moving object is to imagine that the object has been streaked out such that the space between the particles has expanded within the moving object's rest frame. But while this is electrostatically true, mathematically true, it's heuristically false, because for the muon story, this streaked out picture leads to paradoxes in which the Earth's atmosphere stretches out past the moon. In the streaked out picture, the muon looks at the atmosphere moving towards him and imagines what the atmosphere would look like in its rest frame. And the muon sees that the atmospheric particles would be spherical, and the etheric fluid flowing around them is practically stopped because it has become extremely thin and less viscous due to being so spread out. You can use a model like this, figuratively, but I think the other model is much simpler. You don't have to think about the fluid interacting with the muon much more weakly than it would have had it not been so stretched out. I think this sort of description should be never used because it is deliberately more complex than alternative descriptions. It has 2 layers of abstraction rather than 1, and 1 is sufficient to describe the system. It's unnecessarily complex. For example, in 1 layer of abstraction, I see a muon moving towards me and I say it looks contracted and it has a slow clock. The muon looks at me and says that my particles look contracted and have a slow clock. Now, in 2 layers, I see the muon coming towards me, and I imagine that if it were frozen in time, it would look temporarily streaked out in space, but its field would be spherical, not contracted. The muon sees the Earth's atmosphere coming towards it, and it imagines that if the Earth's atmosphere were frozen in time, it would look streaked out in space with larger distances between atmospheric particles with spherical, not contracted fields. I think that the 2-layer explanations are unnecessary. They do not add predictive power, they only add complexity. And they should be thrown in the trash because they only serve to make things seem more complicated than they really are. The takeaway from this, as in the other sections, is that the math can still turn out to be correct, even if the heuristic is wrong or overly complex. And your theory can still be wrong if it has a bad heuristic. I think the last section I have here is on temperature and relativity, another place where it's easy to make mistakes. After a beam of particles is accelerated, it looks colder from the perspective of the laboratory, as in the particles don't look like they are moving much relative to one another in their plane of motion. Likewise, a muon decaying into an electron can be thought of as a particle going through different phases of matter, like solid, liquid, and gas. The faster it moves, the longer it stays solid and cold. This leads to a paradox because relativity tells us that if the muon looks cold to us, then we must also look cold to the muon. This contradicts common sense because if a sensor is colder than its surroundings, it should automatically measure warmth. And many physicists are content to accept such a contradiction and move on. I am not such a person, and I really have to stretch my legs. Are they even going to bend? Oh. Okay. They have gone dead. Okay. This situation of temperature loses its paradoxical nature if you consider that the temperature can be both positive and negative about absolute zero, the coldest temperature possible. Yet, if we only ever talk about the absolute value of temperature, then relativity will suggest paradoxical situations with respect to temperature. We can use an absolute perspective because, and I think we should do this. So, in this sense, relativity is inconsistent with thermodynamics because thermodynamics is based around the idea of absolute zero. There is a temperature. And to understand superconductors, you have to understand how that works. And I made a post on superconductors that you should take a look at. The absolute perspective allows us to see that particles in relative motion are positive cold versus negative cold. And a simple change of scale produces a result consistent with a hot versus cold psychological intuition, thereby removing the contradiction with the relativistic intuition imposed by the condition that the speed of light cannot be exceeded. This ties into the concept of relativistic mass, something that has also been messed up in physics instruction. The alternative to thinking about how the temperature approaches absolute zero as the energy of a relativistic object increases is to talk about an increase of relativistic mass as an object's velocity increases. For some reason, this terminology has gone out of fashion, and students are told that thinking about relativistic mass will confuse them. I find that the opposite is the case. You will get confused if you do not think in terms of relativistic mass. This becomes clear when you learn that when particle beams are accelerated, they get stiffer, as in harder to bend with magnets. This stiffness can be interpreted as an increase in the relativistic mass of the particles, or as an increase in the energy of the particles. The only difference between the two linguistic approaches is that one is given in terms of a concrete thing that you can see and feel, mass, and the other is given in terms of an abstract concept, energy, about which most people have no intuition. There isn't really any reason for the present-day fashion of ranting and raving about relativistic mass being a terrible, misleading concept. The property which increases exponentially is the resistance of space to motion. This is easy to understand intuitively. The massive object is made up of moving space, and moving space cannot move at more than the speed of light, or at more than a maximum speed. The internal motion of the mass at rest tells you how close to that maximum speed you can get before the internal motion breaks apart. In this video, I have explored 8 different situations in which a literal interpretation of the mathematics leads to counterintuitive or paradoxical results. Instead of insisting that because the math works out, the situations cannot be considered to be paradoxical, as is the custom in the present-day physics community, I have insisted that we should demand that our interpretation of the math does not contradict our basic understanding of reality. Reality is our daily experience of how the world works, and illusion is something that contradicts our daily experience, but which can be explained with a deeper understanding of the tricks reality can play. In the case of a particle which appears to length contract because it is traveling at a high rate of speed, we might say that the contraction was an illusion. But if that is the case, that illusion has real physical consequences in terms of the magnetic field of the particle. Thus, it makes sense to figuratively describe length contraction of particles as a feature of reality, whereas under certain circumstances, that's important, whereas the paradoxes which result from this contraction are an illusion caused by poor choice of the words used to interpret the mathematics. I think I said something wrong in that sentence. I should do it again. It makes sense to describe length contraction of particles as a feature of reality, literally under certain narrow sets of conditions, but figuratively in a general sense. That's the way what I wanted to say. Whereas the paradoxes resulting from this contraction are an illusion caused by poor choice of the words used to interpret the mathematics. So far, I have stuck to the convention that the speed of light is constant, while length and time change. But it is also possible to derive all of physics by starting with the assumption that the speed of light changes, but time and length are constant. The convention you choose determines what you think of as reality and what you think of as an illusion. When you decide that the speed of light is constant and time literally dilates, you end up talking about an expanding universe and galaxies full of dark matter, invisible matter that light travels right through, unlike all other matter we've ever seen. You end up having to explain the contradiction that in such a framework, stars are moving away from each other at faster than the speed of light. but that's okay because of the coordinate system that's been chosen. Really, I mean, when you decide that time is an absolute and the speed of light is just a geometric convention, which changes depending on relative speed or gravity, then you find that the universe is not expanding and that there is no dark matter. You end up having to speculate about light gradually losing energy in a non-quantum mechanical fashion as it travels over vast distances. The difference is therefore just a matter of word choice, but one description sounds much more mysterious and full of illusions and paradoxes than the other. I'll go into this in some of my other videos. I think it's called Weary Light, about tired light. And I encourage you to take a look at them. And also the post on superconductivity is helpful for understanding relative temperature. Basically, I'm just pulling this information from my memory of my classroom experience from the pre-internet age. And what you hear in a classroom, it's designed to complement what is in books in terms of helping you develop your intuition. And when I see people answer questions on the internet about physics, I see that large numbers of today's physicists have made it through the system without being able to develop their intuition, as in they didn't have access to a very good classroom experience. And I hope that some of this material I'm putting out here can help you interpret your present confusion with your classroom experience. Because when there are holes in the narrative you are getting, you just start, you get a panic, and you just keep going forwards, just doing the math without understanding really what it's trying to say. And I think I've gotten a feeling for how the pieces of physics connect together just from working in the field and using many different languages to describe one system. You see the weaknesses and the strengths of the different languages and how literal and figurative concepts are used in different contexts. Thank you for watching. Until next time. Well, I hope I wasn't off of the screen.